Hi, welcome back to our last nuclear chemistry video. Today we're going to talk about half-life. We're going to end up doing half-life problems for radioisotopes. You're going to want a calculator today. We're going to look at what half-life is, take a look at our reference table, so you're also going to want your reference table, and do some practice problems, and again, you're going to want your calculator for those. So half-life is the time required for a substance to decay 1/2 of its initial value. This is a method for measuring radioactivity. Half-life is also used with carbon dating and uranium dating, like we saw in our uses for radioisotopes video. So please copy down this table. But every time a half-life occurs, again, half of the material has decayed. So just to reiterate that point, we're going to take a look at the fraction of remaining material. So when no half-lives have passed, you have 100% of your material, or in this case, you start with 1, a whole bit of material. After a half-life passes, you only have half of that material remaining. When another half-life passes, you're going to have half of that sample. A half of a half is a quarter, and so on and so forth. So when the third half-life passes, you're going to have, again, another half of that sample is going to decay. So then you're left with an eighth, and this continues going. So if a fourth half-life passes, then you would only have a 16th of the original amount left. So every half-life that occurs, you lose half of the amount of material. I shouldn't say lose material, half of it decays or transmutates into new material. You should also be able to recognize what this looks like in a graph. So every graph for half-life of any radioisotope is going to show exponential decay, meaning it's going to have this shape. The time and amount can change on the y and x axes, but overall it's always going to be an exponential decay for a half-life graph. You're going to need your reference table because we're going to be using table N, our selected radioisotopes table, because it provides the decay mode as well as the half-life lengths on this table. So if you take a look right here, we have our list of half-lives for our various nuclides. You can see that half-life has a wide range in terms of time. Like if you take a look, we have something as small as milliseconds, decays very quickly into thousands and thousands of years for the half-life. So if you think back to our last video, this is why some of these isotopes are useful for medical purposes, because some of them last only seconds or minutes, hours, maybe a few days, but others would not be useful because they last years, and years of exposure to radioactivity would be detrimental to your health. So I'm going to walk you through a half-life problem. We're going to use a table to solve these problems because I think it's the most straightforward way to do it at this point. There is a half-life equation that I'm not going to teach you because it relies on natural logs, and not everyone has covered Algebra 2 yet. But let's take a look at a pretty typical question. A 62-gram sample of iron 53 decays for 34.04 minutes. What is the mass of iron remaining? So if you take a look, this is the table we're going to use for each of these problems. It has 4 categories: half-lives that pass, the time that passes, the amount of mass that decays, and the fraction remaining of that sample. Key pieces of information from the actual question: our starting mass is 62 grams. So our iron 53 radioisotope started at 62 grams. The overall time of decaying is 34.04 minutes, so this is going to be our stopping points in terms of time. And we can look up that half-life of iron 53 using table N. So if you come to table N, we find iron 53, we see that its half-life is 8.51 minutes. So there is additional information that you're going to have to be able to pull from your reference table for these problems. So when starting this table, there's some information that's always going to remain the same to start with. You always start with 0 half-lives. So as in no half-lives have occurred yet. The time is always going to start at 0. The mass, so our starting mass is going to be whatever is given to us in the problem. So we're starting with the 62 grams this time. And our fraction always starts at 1. We always start with the whole amount. So 0 for half-life, 0 for time, 1 for the fraction. You always start with these values in any problem you're doing. The biggest mistake I see is people tend to start at half-lives 1. 1 hasn't occurred yet. We're starting at 0 half-lives. And I also see people not start at time 0. You're always starting at time 0. So try to remember these values. Now we're going to fill out each column. So when 1 half-lives pass, it takes 8.51 minutes. So again, that time, every half-life, 8.51 minutes for this substance. Whenever a half-life occurs, we end up with half of the mass of our sample, so 62 divided by 2. We have 31 grams left of our sample, and the fraction remaining is half. We're going to repeat the process, so a second half-life passes. Another 8.51 minutes has passed, so 8.51 plus 8.51 is 17.02 minutes. We now have half of our mass, so 31 divided by 2 is 15.5 grams, and we only have a quarter of our initial substance remaining. But I know I need to keep going because we still haven't reached that 34.04 minutes of time elapsed. So half-life 3 occurs. It takes another 8.51 minutes for a total of 25.3 minutes passed. Half of our sample has now decayed, so we're left with 7.75 grams of iron 53, and we're left with an eighth of our original sample. We now move on, and another half-life passes. An additional 8.51 minutes passes, and we're now at our stopping time, 34.04. Half of our mass remains, and a total of 1/16, that should say 1/16, of our original sample remains. So to answer the question, what mass of iron remains? Iron 53, there's 3.875 grams left. So almost the same question, but a 62 gram sample of iron 53 decays for 34.04 minutes. The exact same setup as the last question. But what fraction of the original amount remains? This is why I like doing the table, because even though you might be doing what seems like additional work by including every category in that table, most of the time these are multi-part questions, and part of that table will answer the next question. So in this case, what fraction of the original amount remains? Let's go back to look at our table. Oops. If we take a look, at 34.04 minutes, we're left with 1/16 of our original mass. So the answer to what fraction of the original amount remains is 1/16. Here's another example. So an 80 gram sample of a radioactive isotope decays to 5 milligrams in 32 days. What is the half-life? So this time we're not given what the isotope is or what the half-life is, but we're going to figure out the half-life. So to solve this problem, we're going to have to work backwards. I'm going to give you a second to give it a shot, and then I'm going to go over it. Alright, so here we go. So half-lives, I've just gone 0 through 5. I'm not sure if it's actually going to take 5 whole half-lives, but things to start with. You always start at 0 half-lives, you always start at time 0, and you're always going to start with the whole amount, or 1, with 100% of your material. We're starting with an 80 milligram sample of the radioisotope, so I filled in 80 milligrams to start with. And we know it's going to decay until it reaches 5 milligrams, and it takes 32 days in order to do so. So because I know the stopping point for the mass, that's actually the category I'm going to start with. So when one half-life passes, we're left with 40 milligrams. When another passes, we're left with 20. And every half-life we keep having until we reach 5 milligrams, which is our stopping point. So now I can see that this isotope goes through 4 half-lives in order to decay from 80 milligrams to 5 milligrams. I can easily fill in the fractions now as well, just to get that out of the way. Half, quarter, eighth, 16th. And lastly, now I have to figure out the time. So I know it takes 32 days, so 32 days is my endpoint. This material has gone through 4 half-lives, so each half-life has to take 8 days, because 32 divided by 4 is 8. And if we fill that in, we can see each one is 8 days, so the half-life for this material is 8 days. Alright, I've walked you through a couple half-life examples. There's going to be practice questions on this topic shortly. If you have any questions, as always, feel free to reach out to me. Otherwise, have a wonderful day.